Hey guys, it's John the Quant here. Hopefully you're coming straight over from the last video where we did our first Ito integral. And so you know that we're doing iPad only because I'm traveling right now. Hopefully I'll be home again in the next couple of days and we can start doing videos where you can see me again. But today what we're going to talk about is Ito's lemma. We're going to derive it in a very non-rigorous way, but you're really going to get to see what's happening underneath and kind of understand where all of this stuff comes from. Now, Ito's lemma is probably the most important thing in stochastic calculus because without it, there's not a whole lot else that we could do. And we're going to start with a stochastic differential equation. Stochastic differential equation. And it's going to look like this. I'm being very explicit here. X of t is equal to the integral from 0 to t of a, which is a function of x, and s, ds, plus the integral from 0 to t of b, which is also a function of x, and s, db. Now this first part here is deterministic. It is not random at all. And this second part, well, that's that Ito integral, like we did in the last video. See, so b of s is a standard Brownian motion. And this whole thing, a deterministic part plus a stochastic part, is called an Ito process. Now, most often, what we are referring to is this whole thing, but the way you'll see it written, if you're lucky, is dx of t equals a of x of t and t, dt plus b of x and t, db of t. But most of the time, we'll go even more shorthand, and we'll say dx equals a dt plus b db. So when we write this, we really mean this. And this one can be super confusing for beginners. I know that when I was first starting to learn this stuff, I was so confused. I had no idea what people were talking about, and it's because they were using this shorthand. That's why I'm trying to be as explicit as possible most often. So now, we're going to imagine another function, y of t, which is defined to be equivalent to some function f of x and t. And so, Ito's lemma tells us that dy of t has stochastic differential equation representation that looks like this. dy equals a sub y dt plus b sub y db. And if we're going to be a little more explicit there, going the other way from before, dy of t equals a sub y, which is a function of x, t, and f, dt plus b of y, which is also a function of x, t, and f, and when we say f here, we mean this function up here. So one more step out, y of t is equal to the integral from 0 to t of a of x of s, s and f ds, plus the integral from 0 to t of b, sorry, these should have sub y's on them, of x of s, s and f db of s. So again, we're going to write this, but we really mean this. And furthermore, Ito's lemma tells us what a of y and b of y actually look like. And it says that a of y is equal to the partial of f with respect to t plus the original a, which is a function of x and t, times the derivative of f with respect to x, plus 1/2 the original b, which is a function of x and t, squared, times the second derivative with respect to x. And b of y is equal to the original b, which is a function of x and t, times the first derivative of f with respect to x. So the whole thing altogether tells us that dy is equal to the partial of f with respect to t plus a, which is a function of x and t, times the derivative of f with respect to x, plus 1/2 the original b squared, times the second derivative of f with respect to x dt, plus the original b times the first derivative of f with respect to x db. How are you guys feeling right now? Hopefully you feel good. Let me know if you're confused at this point. Now we're going to look at why. Why does dy have this stochastic differential form here? And to answer that, we're going to start with a Taylor series. Now let's say that the absolute value of h is like really, really close to 0, but h is not actually equal to 0. So think of this as maybe the limit as h approaches 0. Then we'll have f of x of t plus h equal to f of x of t. This is just a Taylor series, okay? Plus x of t plus h minus x of t times the first derivative of f with respect to x evaluated at x of t plus 1/2 x of t plus h minus x of t squared times the second derivative of f with respect to x, evaluate that at x of t, plus some other stuff at the end there. But we're only going to keep the first two terms because really the approximation is close enough at that point. So let's just move this to the other side. F of x of t plus h minus f of x of t is then equal to x of t plus h minus x of t times that first derivative evaluated at x of t plus 1/2 x of t plus h minus x of t quantity squared times that second derivative of f with respect to x, evaluate that at x of t, plus some other stuff. And we're not going to talk about that other stuff anymore. Now let's look at the next step, f of x plus 2h. So if you think about this, t plus 2h minus t plus h is just going to give us h, which is the same as t plus h minus t. So we can still do this. F of x of t plus 2h minus f of x of t plus h is going to give us x of t plus 2h minus x of t plus h times that first derivative of f with respect to x evaluated at x of t plus h plus 1/2 this next part, x of t plus 2h minus x of t plus h, we got to write real small here, squared, the second derivative, evaluate that at x of t plus h. Now let's add these two together. We're adding these two things together here. So on the left, we'd have f of x of t plus h minus f of x of t plus f of x of t plus 2h minus f of x of t plus h. And you guys can see that these two things are going to cancel out. And so we're going to get f of x of t plus 2h minus f of x of t. And on the right, I'm going to write it like this. I'm going to write the sum from j equals 0 to 1 of x of t plus j plus 1 h minus x of t plus jh times the first derivative evaluated at x of t plus j h plus 1/2 the sum from j equals 0 to 1 of x of t plus j plus 1 h minus x of t plus jh squared times that second derivative. And that's also evaluated at x of t plus jh. And we're using this sum because we're about to just sum up a ton of these things. An absolute ton of f of x of t plus jh's. So we keep going, and everything's going to kind of cancel out like it did up here, and we'll eventually get f of x of t plus nh minus f of x of t is equal to the sum from j equals 0 to n minus 1 of x of t plus j plus 1 h minus x of t plus jh times that first derivative. Evaluate that at x of t plus jh plus the sum from j equals 0 to n minus 1 of x of t plus j plus 1 h minus x of t plus jh. Square that times the second derivative. Evaluate that at x of t plus jh. Now let's take just this front part, and I'm going to change the notation a little bit. I'm writing the same thing, I'm just changing how we write about it to make it a little easier to work with. So this is the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j times the first derivative with respect to x, and evaluated that at x of t sub j. Now if you think back to that last video on the Ito calculus, which if you haven't watched, I definitely recommend you go back, what we're really doing here, this is the same as the integral from 0 to t, or sorry, from t to t plus delta t, okay, of the derivative of f with respect to x dx. Where if you think about it, this first part, that would be the width of a rectangle, and this is the height of a rectangle. Where we've got some function here and we're drawing these rectangles to try to, and then add them up, like we did in that last video. So right now, what we've got is f of x of t plus nh minus f of x of t is equal to the integral from 0 to t, or t to t plus delta t. I'm sorry, I keep misspeaking a little, of the derivative of f with respect to x dx of s, plus this sum, 1/2 times the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j squared times the second derivative of f with respect to x, evaluated at x of t sub j. Now I want to talk just about this. We're going to do another approximation. And that is, we're going to say that the second derivative with respect to x, when we evaluate that at x of t sub j, is equal to the second derivative of f with respect to x evaluated at x of t for all t sub j. And we can say that because it's the second derivative, it's pretty smooth, and this approximation is getting us as close as we really need to be. So we can rewrite that now. F of x of t plus nh minus f of x of t is the integral from t to t plus delta t of the derivative of f with respect to x dx, plus 1/2. We can factor out that second derivative now that we're all saying they're all the same. Second derivative of x, evaluated x of t, times the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j squared. Now this one, we're going to have to deal with. We'll do that in a minute. This one down here, f of x of t plus nh, is actually just exactly the same as f of x of t plus delta t. You see this part inside here corresponds to this. That part corresponds to that one. So let's pull this part that we've got to deal with. Let's just pull that out and we'll think of it by itself. All right, so that's the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j squared. We're going to use something called the mean square limit. And to do this, we're going to think about this thing right here as, think of it as a random variable with mean t. And so how would you find the variance of a random variable? Let's say it's q. We'll call this q. Well, that's the expected value of q minus mu squared, right? So in this case, we have the expected value of our q, which is the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j squared minus mu, which is t. This whole thing together, square it. So the mean square, and then limit is that eventually we're going to talk about the limit as n approaches infinity, but don't worry about that too much right now. What we're going to do first is we need to expand this. And I'm going to drop the expected value notation. So we're just going to be dealing with the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j, totally squared, minus t, and then square that. And when we expand this, we're going to get... Oh man, guys, I really messed this up. So I'm going to go back a little bit. We'll just make it go a little faster. All right, it'll be okay. Bye. We're going to expand this here, and we will get the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j squared, squared again, minus 2t times the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j squared plus t squared. Now we can take this part and expand again. And when we do that, we will get the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j to the fourth plus 2, the sum from I equals 0 to n minus 1 times the sum of all j less than I of x of t sub I plus 1 minus x of t sub I, square that, times the x of t sub j plus 1 minus x of t sub j squared. Then we have this part here again. 2t sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j squared plus t squared. And all of this is in the expected value. So this is all in the expected value. And we can handle that in pieces. So our first piece here, let's do that. The expected value of the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j, totally to the fourth, well, we can take that sum outside. And then here, because this is a standard Brownian motion, we know that x of t sub j plus 1 minus x of t sub j follows a normal distribution with mean 0 and variance t over n. So we've got the expected value of a normal 0 t over n to the fourth, which, if you watched that last video, we're doing all the same tricks that we did there. Pull that out. Now we have square root of t over n times a standard normal altogether to the fourth, which is, we'll put the fourth through, t squared over n squared times a normal 0, 1 to the fourth, which is t squared over n squared times the expected value of a normal distribution to the fourth. And the expected value of a normal distribution to the fourth is 3 sigma squared, where our sigma squared in this case is 1, so that's just the 3. So altogether we have 3t squared over n squared. So for now, our first part is the sum from j equals 0 to n minus 1 of 3t squared over n squared. And then we still have the other pieces. I equals 0 to n minus 1, sum over all j less than I of x of t sub I plus 1 minus x of t sub I. Square that. T sub j plus 1 minus x of t sub j. Square that. Minus 2t, sum from j equals 0 to n minus 1. A lot of sums in this. Plus t squared. And look at this. We got kind of the same thing. This is still in the expected value, right? And we've got kind of the same thing happening repeatedly. So let's just deal with that. Let's deal with the expected value of the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j squared. Well, again, we can pull the sum outside. X of t sub j plus 1 minus x of t sub j squared. This, again, is normal, 0 and t over n. So we've got, I'm dropping the sum here, the expected value of a normal with 0 and t over n squared. Same trick as before. Square root of t over n times the standard normal squared. Square that and bring it outside all in one move. I think we can handle that. Expected value of a normal, standard normal squared, which becomes the expected value of a chi-square with 1 degree of freedom, which is just 1. So we've got here t over n for our expected value of that thing. Let's write it all out. The expected value of the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j squared is equal to t over n. So now let's rewrite the whole thing. We have the sum from j equals 0 to n minus 1 of 3t squared over n squared plus 2 times the sum from I equals 0 to n minus 1 times the sum from j less than I of t over n times t over n minus 2t times t over n plus t squared. I'm sorry, this is a sum. Sum from j equals 0 to n minus 1. Sorry about that. Now this sum has n terms. This sum has n terms. And these two actually have n times n minus 1 over 2 terms. And they're all constant. Nothing's changing inside there. So we're going to end up with n times 3t squared over n squared plus 2 n times n minus 1 over 2 times t squared over n squared minus 2nt times t over n plus t squared. Now hopefully you can see some of this stuff is going to simplify out here. For instance, we'll have 3t squared over n plus those two 2's are going to simplify away. And that's n times n minus 1 times t squared over n squared minus 2. These n's are going away, t squared plus t squared. Keep simplifying everything until you're done. N squared minus n times t squared over n squared minus t squared. 3t squared over n plus, when we multiply through, these are going to cancel out. You're going to get plus t squared minus t squared over n, and then minus t squared. Those will go away. And these can actually be combined to be 2t squared over n. Now the limit, now is when the limit comes in. As n approaches infinity of 2t squared over n is 0. So the expected value of the whole thing, that is the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j squared minus t totally squared is 0. So in the mean square limit, and those words are important, in the mean square limit, the sum from j equals 0 to n minus 1 of x of t sub j plus 1 minus x of t sub j totally squared is equal to t. Or in our case, it's actually equal to delta t. Now, I've been writing t because we usually would integrate from 0 to t, but in our case, we are going from t to delta t. So this implies that the integral from 0 to t, should we write that as a regular t? This, as written, implies that the integral from 0 to t of dx of s squared is equal to t. But what we're really doing is the integral from t to t plus delta t of dx of s squared is equal to delta t. Now let's see how we can use that by going all the way back here to our f of x of t plus delta t minus f of x of t is equal to the integral from from t to t plus delta t of that first derivative of f with respect to x dx plus 1/2 the second derivative of f with respect to x times delta t. So now we can write this as df of t is equal to the integral from t to t plus delta t of the derivative of f with respect to x dx of s plus 1/2 the integral from t to t plus delta t of the second derivative of f with respect to x ds. And this is Ito's lemma here. You will more often see it written like this: df equals the partial with respect to x dx plus 1/2 the second derivative with respect to x dt. And these are the same thing. And there we are. Hopefully you guys feel good. Let me know if you got lost anywhere, all right? We're just going to do one more thing real quick. We're going to do an example. we're going to say that f is equal to x squared. So the partial of f with respect to x is 2x. And the second derivative of f with respect to x is just 2. So using Ito's lemma, which says that df is equal to the first derivative with respect to x, dx, plus 1/2 the second derivative with respect to x, dt, we can start plugging things in here. We'll have df is equal to 2x dx plus 1/2 times 2 dt. These two things will cancel away. I messed up again, but I fixed it, so go ahead and finish the rest of the video. So if we're going from 0 to t, then we'll have f of x of t minus f of x of 0 is equal to the integral from 0 to t of 2x of s dx of s plus the integral from 0 to t of just ds. Now we know that f of x is equal to x squared. So here we just have x squared, and here we have 0. And here we can factor this to the front, 0 to t of x of s dx of s, plus we can do this integral actually, and we know we're just going to get t. So we have now x squared equals 2 times the integral from 0 to t of x of s dx of s plus t. We can move this over. X squared minus t equals 2. Integral from 0 to t of x of s dx of s. Divide by 2. We get x squared over 2 minus t over 2 is the answer for our integral from 0 to t of x of s dx of s, which is the same answer as in the last video. So hopefully you guys feel pretty good. We're going to do another video in just a minute about deriving the Black-Scholes stochastic differential equation. It's going to be a great video. If you learned something in this one, please like. If you want to catch that Black-Scholes video, subscribe. Like I said, I should be back home and doing these where you can actually see me in a couple of days. So have a good day, guys.